Professor Amitabh Banerji from University of Potsdam on curriculum innovation research from low-cost experiments to high-tech applications. Professor Banerji studied chemistry and computer science for teaching at grammar schools and completed his legal clerkship at the Herder Gymnasium in Berlin-Charlottenburg. From 2009 to 2012, he received his doctorate in the working group of Professor Michael Tosh at the University of Wuppertal on the experimental didactic indexing of organic light-emitting diodes. He then worked for 2 years as a lecturer and a specialist coordinator at the Junior University of Wuppertal. In 2014, he joined as an assistant professor for chemistry education at the University of Cologne. Since 2019, Banerji has been a university professor in chemistry education at the University of Potsdam, where his research focuses on curriculum innovation and research-based implementation and digital tools in science education and chemistry. He has won several awards, including the highly commended project at the European Science on Stage Festival, Debrecen and Brandenburger Innovationspreis Cluster Kunststoffe and Chemie 2021, awarded by the Ministry of Commerce and Energy in Brandenburg for the project Box Experiment. Over to you, Amitabh.
Thank you. So, is the microphone on? Thank you. Thank you, Mashood. Okay, yes. Thank you for this nice introduction and warm welcome also from my side. I'm very happy to be here and have the opportunity to talk to you. It's actually my second time I'm performing on this stage. It was back 2017 when Arnab invited me and we had a collaborative project. I will talk about this later. Today I'm going to show you some research highlights, and to connect to my previous talker, even if I may look like an Indian, inside I'm more a German because I was born in India, but when I was 4 years old, my parents shifted to Berlin, to Germany, and I was basically brought up in Germany. I speak Bengali because Banerji, I'm from a Bengali family, but I cannot read or write it, so I only learned it by listening. So my today's talk will be on curriculum innovation research, and actually I have to admit I had to change my subtitle. Where's my pointer? Because I'm not really happy with this subtitle. After listening yesterday's talks, there was several good talks also, and I listened to one talk where the phrase came up, Mazaya. I think it was the talk about astronomy by Dasgupta, and that's why I changed my subtitle, Development and Implementation of Mazaya Experiments, yeah? Because this is actually what we are looking for, yeah? We can do a lot of large-scale empirical researches, but if we have this moment, Mazaya, then we know, okay, they have fun, yeah? So, and my talk is about something which gets a little bit neglected, and this is the development of teaching materials and experiments. Yeah, we always talk about research and development, R&D, but the focus always lies on the R, the research. But without good developments, there is no research. And without research, the developments will always be on a prototype state. So today's talk is dedicated to the development of Mazaya experiments, and we are working on a framework in Potsdam which follows 5 steps to get to such experiments. And this starts with an inspiration, and I will talk about some theory on organic semiconductors. This is the topic I would like to present to you. This is one of our oldest or most successful topics which we conducted in the last 10 years. The second phase is the invention. And here we do some DIY experiments, do-it-yourself experiments on innovative research topics. And the third phase is the investigation and the instrumentation. And the last one is the implementation of these things into schools or other educational institutions. So let's start with the first step. And I would like to talk about organic semiconductors. This is something in between physics and chemistry, because semiconductors normally belong to physics classes. And I don't know how it's in India, but in Germany, semiconductors are not taught very well. It's only a very little part of the curriculum in physics or in chemistry. And this is something which is lacking because our society has a big demand for semiconductors. Without semiconductors, we are not able to have smartphones. We are not able to have solar cells, transistors. All the microprocessors are based on semiconductors. So we need to learn more about semiconductors. And so far, inorganic semiconductors like silicon or gallium arsenide were well established, but because of our hunger for semiconductors, we are running short of these materials, and we have to come up with new ideas to build or synthesize semiconductors. And organic semiconductors are a new type of semiconductors. And the two products we are going to talk about are OLED displays, organic LED displays, and organic photovoltaics. So let's dig into these two topics. So first, OLED displays. I will use a picture from LG, which you see here in the upper part, an LCD panel, and here an OLED panel. And I'm not going into details, but in an LCD panel, you have several layers and a backlight, which is giving white light shining through all these layers. Here is a key layer, which is a liquid crystal phase, giving also the name liquid crystal display. And this liquid crystals, simply spoken, decide whether the light can pass through, the white light can pass through or not. And if the light can pass through, then it got colored, or the wavelengths got be isolated, which are desired, like blue, red, or green, or red, green, blue, RGB. And by additive color mixing, you get the picture in front of the panel. So this is the old LCD technology, and the newer technology is the OLED technology, which does not use any backlight and only has a few layers. And the pixels itself, they are emitting like very small OLED pixels. And in this case, we have a very, very thin panel, which leads to very innovative applications like transparent displays. And I will use this small video to show you an example.
This is a new organic light-emitting diode screen from Samsung. It's hot off the presses from Korea. It doesn't have a name or a price or anything like that yet. It's 14 inches. Right now they kind of attach it to this laptop. As you can see, it's transparent. It's actually 40% transparent. When you turn it on, you get this. This is freaking amazing. This may look like a prop from Avatar, but it's not. This is real. You get 100,000 to 1 contrast ratio. You see, it's still transparent. You can see my hand moving in the background.
So yeah, this video is more than 15 years old, by the way. So at that time, that was a very innovative thing. Nowadays, we have applications like augmented reality. You have goggles or glasses where you can see through, and you have digital information. Another thing are flexible displays.
Hey guys, it's Max with PhoneArena.com. We're in San Francisco with LG, and we're just going to show off this super flexible display that is underneath the LG G Flex. This is the actual display itself. First of all, while it's running this video script here, just look, first of all, at how thin this thing is. The camera doesn't do it justice, but holding it in my hand, it's like paper thin times 2, and that's about it. Super thin and also very flexible. So here we are looking at all this great video here, and I'm just going to take this display and I'm going to bend it. I'm going to keep bending it. I'm going to make the engineer over here very nervous as I do that here on video. But he assured me I couldn't break it.
Yes, so also this video is more than 15 years old. At that time, the technology was very new, and nowadays you find it everywhere, like the Samsung foldable phones or tablets. So this is something which was very interesting, and we thought about, are there any good experiments to show the principles of these semiconductors? And we found nothing for the educational area. So what we did is we worked together with a scientific institution in Potsdam, the Fraunhofer Institute for Applied Polymer Research. And they have recorded a very nice image film about OLED. And it's about 5 minutes. And I would like to invite you to watch the first 3 minutes, because it's very vividly explained what organic semiconductors are and how an OLED is built in a research lab. So in the video, they call the OLED a PLED because of polymer LED. There are different abbreviations, PLED or OLED, because there are also smaller molecules, organic molecules, but we rely on polymeric. So they are speaking of PLEDs.
Scientists and technicians at the Fraunhofer Institute for Applied Polymer Research are working on the next generation of flat panel displays based on polymer materials. This new technology is called light-emitting diodes based on polymer materials, short PLED. The PLED story began in 1989 in the Cavendish Laboratory in Cambridge in the United Kingdom. By chance, scientists discovered that polymers are able to emit light. An important step for the development of new displays is the development of new materials with improved purity. The Fraunhofer IAP is concentrating on producing ultra-pure and defect-free materials on lab scale. Small units of organic molecules are synthesized to larger units to control the charge transport and the wavelength of the emitted light. In this way, the polymer material gets more functionality. The newly developed polymers have one thing in common: many double bonds and aromatic rings, also known as conjugated p-electron systems. These conjugated materials are used for PLED devices because of their superior solubility, which makes them easy to deposit. The polymer materials are dissolved in special solutions, which allows to produce very thin layers of about 100 nanometers in a spin coating process. Spin coating is also a very easy process that allows to bring the PLEDs into different applications. Besides the polymer layer, a lot of other layers are necessary for a PLED device to emit light with high brightness. Transparent and reflective layers are used for the outcoupling of light. Other layers will be introduced to increase the efficiency and lifetime of PLEDs. The simplest PLEDs consist of an organic layer which is situated between two electrodes, anode and cathode. When a very low voltage is applied to the PLED, it starts emitting light. It is visible through the transparent layer. The color of the PLED is controlled by the polymer structure.
Okay, I'm interrupting this video at this point, and let's summarize the key messages. So first of all, how is an OLED built? The bottom of the OLED is a glass, or if you have a flexible OLED, a PET foil, for instance. But it's not a normal glass, it's a conductive glass. And the conductivity is reached by using ITO or FTO, which is indium tin oxide or fluorine-doped tin oxide. And everybody knows this glass because you have it on your mobile phones. Yeah? The touch display works on the principle of conductive glass. So on top of this glass, you apply the semiconductor layer. And as you have seen it in the video, it has to be very thin, like only 100 nanometers max, because otherwise it will become an insulator. So one technique to apply this is the spin coating process. And on top of the semiconductor, you apply the metal counter electrode. And this is usually done in the high vacuum by evaporating the metal. So very sophisticated steps, and I will come to that in a minute. But let's see what happens when we attach power source to our OLED. So you have the plus pole on the ITO side and the minus pole on the metal side. And the next steps are charge injections. On the negative pole, electrons are ejected into the semiconductor. And on the positive pole, holes, so-called holes, are injected into the semiconductor layer. These charge carriers drift to each other in the electrical field. And by chance, they will recombine. And by this recombination, you can get light out of it. And the light can be outcoupled through the transparent electrode. So this is also a very basic property of semiconductors. It can help electrons and holes, it can transport them, and it can interact with light. But why is this semiconductor, an organic semiconductor, able to do that? It's because of its specific structure. It's a conjugated double bond system. In other words, it's a chromophore. But instead of using a dye molecule only, we also have a polymer molecule. So we have the combination of a dye molecule and a polymer molecule, which leads to a semiconductor. Because a polymer molecule has a very large backbone, so the charges can be transported over a significant distance, which is necessary to get to a device. And this conjugated system, the pi electrons are delocalized over the whole backbone, which leads to electrical conductivity. So let's move on to organic photovoltaic, because if you have understood the basic principle of an OLED, it's very easy to understand what a photovoltaic cell is working. So far we are based on the silicon technology, for instance, solar cells on the rooftops. But by using organic semiconductors, we are able to produce lightweight, semi-transparent solar cells which can cover the whole building, especially high-rise buildings are very interesting. You can cover the whole facade, and by using this whole surface area, you can generate much more power, electrical power. So this is a hope for the energy transition. So how does an OPV cell work? If you have here the sketch, again, the first thing is we have to absorb light. So light is shining through the transparent electrode and is being absorbed by the semiconductor material, gaining an electron-hole pair. And now this is the difficult part. How can you separate electrons and holes? I will come to this in a minute. But if you are able to separate those charge carriers, then you are able to bring them to an outer circuit where you have, for instance, a consumer or a battery, and you can use this light energy to store or drive some consumer. So how do you get electrons and holes separated? For this, you need a so-called donor-acceptor system. The donor molecule is, again, a conjugated polymer molecule, which has a high absorption coefficient, so it can absorb sunlight very efficiently, gaining an electron-hole pair. The electron is then very quickly transferred to an acceptor molecule, which is here a fullerene derivative. And this derivative, this material, has a very high electron affinity. So it catches the electron in a femtosecond process, and then electron and holes are separated from each other. So this is a very quick overview about the basic functional principles theory of organic semiconductors. And now I would like to move on to the invention part. So in the invention part, we think about how to transform this sophisticated, high lab standard experiments into a hands-on, into a Messiah experiment. So we have identified some steps or some criteria we have to think about. First of all, low cost, because also in Germany, schools don't have money. So it has to be a very low-cost approach. Low risk. In contrast to high-standard research laboratories, we are not allowed in schools to work with all kinds of chemicals. So we have to take care of low-risk assessments. And also the time. Yeah? You have like 90 minutes for a standard lab session. Yeah? So we have to scale down the experiment so it can be done in a reasonable time, let's say 90 minutes max. And low tech, that means that the students performing the experiments are not experts. They are beginners, laymen. So we need to keep all steps as simple as possible. And low scale is, we want to educate them to be environmental friendly. So reduce all amounts, scale it down to a minimum. We have actually some experiments which can be performed in a drop. It's called lab in a drop. So low scale automatically also reduce cost and risk. So this is also something we try to approach. So let me introduce you the hands-on OLED. The hands-on OLED device is constructed by a small FTO glass, which is like 3.5 into 3.5 centimeters. And this glass already has this ITO layer on it. We buy it like this. And first of all, we need to clean that glass. And then the second step, we use an additional material, which is P.PSS. It's a high conductive polymer material. And this just improves the contact between those layers, and this enhances the performance. And then we use the semiconductor, and we spin coat the semiconductor, and then as a top electrode, we use a special material which is Galenstan. I will explain it to you in a minute. So actually, I would like to show the experiment in a live video feed. So this is my camera, and I would like to start by identifying which side of this glass, because you cannot see this FTO layer. You have to identify where it is. So I will just measure the resistance. It is upside down. 1 second. Okay. So I will just measure the resistance of the glass by holding my clips here. I can measure anything on this side. Let's see here. Yeah, you can see there's a measurable resistance. So this side seems to be the one which is conductive. So the next step is that I have to clean the glass. You saw that an OLED is fabricated in a glass box normally. So normally you want to get rid of any dust, any grease, anything which is disturbing the 100 nanometer layer. So let's try to be clean as possible. But we always say it's a quick and dirty experiment, but let's try to keep it as clean as possible. So the first thing is I take a little bit acetone to clean the glass. Just pour it on top of it. And then I need a tissue like this. And then I'm just cleaning the glass from both sides. Okay. So the next thing I need to do, I hope it's now clean enough. I'm just putting a piece of sellotape on one end of the glass. So this is necessary, just to remind you. I go back to the slides. At the end of the day, I need here one part of the glass which is not covered to clip an alligator clip at that point. So this is the reason why I just put a small piece of sellotape here. So the next thing is to apply this P.PSS. This is a very blackish material. It's harmless, actually. You can work with this without using gloves. You can put on gloves, but I've done it so many times, so I don't use the gloves anymore. So you just apply a little bit of this material, and then we use a microscope slide to conduct a technique which is called doctor blading. So we just use a microscope slide, and then just pour everything to the side. And you may think that there's nothing left on top of this glass, but we are on a nanometer scale. So there's enough material on this glass. I now need to get rid of the water. So I'm just using a hairdryer. Okay, so this should be sufficient using a new tissue. So, okay, this is now my prepared glass, which has already the ITO layer and the second layer, the P.PSS. This next layer is the semiconductor. And the semiconductor needs to be spin coated. In the development process of this experiment, we tried different things, like just paint brushing it or just dipping it. And nothing worked so good as a spin coating process. The problem was that spin coaters are very expensive. So normally they cost like between 1,000 to 3,000 euros. So we think about alternatives. And after a long process, actually there were 2 or 3 bachelor theses on this problem. We came up with this idea using just a PC fan. This is just a PC fan. And we connected this PC fan to a 4.5 volt battery, because the voltage of the battery determines the speed of this spin coater. So we attached this glass with a double-sided tape. You see, this is a double-sided tape. And then we just connect it to the battery. And you see it's starting to rotate. So I have a splash protection. It's just a bottleneck. So we have this bottle, and you can see it's now running. And I can use now my semiconductor, which is this liquid. It's solved in toluene. So if you are working on a larger scale, you should use it under a fume hood or outside. But I will only use 0.1 milliliters, so very, very low scale. And so I will do it here on the stage. Let me just get the material. And I will tilt the camera so you can better see the process. Okay, like this should be enough. Now I have to be careful to target the middle point, the rotating middle. Okay, so this is now applied, the solution, and by turning it in a very high speed, it's like 1,500 rotations per minute, the solvent gets evaporated and only the polymer layer stays on the glass. So let's have a look. I think this should be sufficient. I just deattached the battery. And now let's see the result of the spin coating process. And there you go. We have spin coated for only €2. So instead of 3,000 euros. So this is the cheapest spin coater maybe, and it works like a charm. So the layer thickness we have checked is about, varies between 70 and 120 nanometers. So on some points it may be thicker, and some points it may be not thinner. So the last step is now we have achieved the semiconductor layer, and now the metal layer is missing. So this was a bigger problem because we tried everything. We melted the lithium to have a liquid metal which we applied on top of it, but it burned everything, and also it got ignited. So at the end of the day, we also tried mercury, because mercury is liquid. It also worked, but of course mercury is too hazardous. It's toxic, we cannot use. But we came up with this material. This is gallium, which is gallium, indium, and tin stannum. And this mixture is liquid at room temperature and stays liquid. And it's not has no hazardous signs, so we can use it also with students. But to apply it to on top of this on top of the layer, we need some kind of a mask. So we have built this small mask. It's just a half of a microscope slide. You have here some spacers, which is just a thicker tape, and you have copper feeds so that we can contact our Gallium points. So what I now do is I just apply this Gallium on these copper feeds, and you can maybe see that this is liquid. I don't need much of it, just a little bit. The nice thing is I can reuse it after the experiment is done. So I now take this glass, I turn it upside down, and then I contact this metal layer, and you can see that I got here a very nice contact without destroying the 100 nanometer polymer layer. So I just take now 2 clips, attach it to the OLED device, and I'm ready to go, and hopefully we will see I will be able to drive this OLED with a 9-volt battery. Let's see if it works. So first of all, I contact the positive pole, and now I would ask the technician to dim the light. In Hindi, आप ये light थोड़ा सा dim कर दो, बंद कर दो. Thank you. Total बंद कर दो, please. हाँ. Oh yeah, okay. This is maybe a little bit too much, but I will try. I will try. Okay, you can see here. This is the first spot. This is the second spot. Oh yeah, thank you. Yeah, this is good. Thank you. So again, this is the first spot. This is the second spot. So the light will always come out on this. Yeah, thank you. Yeah, the light will always come out on the surface of the Gallium. So the surface defines the area which will give you light. So the third one is also working, but not so good. I think the layer may be too thick at that in the third one. So this is also why I put 3 different smaller OLEDs, so I have a better chance that one of these 3 is working. Thank you. So light फिर on कर दो. Thank you. So it looks like it was a very easy going to develop these kinds of experiments, but believe me, it was a long process because we had prototype 1, 2, 3, 4, 100, and so on. And after a long journey, we came up with this final prototype or final version, which is very reliable, and students can perform these experiments by themselves. So let me quickly go to the next. So this was my safe picture if it's not working, but it worked. How to build an organic solar cell. Because students are also very interested in solar cells and alternative solar cells because it's very close to climate change, energy transition, and so on and so forth. So I would like to show you also this experiment. And for this, I already prepared the glass. This camera again. So I already prepared the glass, so it is already washed with acetone, and the P.PSS layer is also applied. So we can directly start to spin coat. And instead of using this emitter polymer, this yellowish, I will use this donor acceptor system, which is here in this vial. And as you can see, this system is very reddish dark, but the process is the same thing. I will just start the spin coat here. Sorry. And then I will apply 0.1 milliliters of this donor acceptor system. So okay, so there's one difference between the OLED experiment and the solar cell experiment. The OLED experiment was only one component, which is this PPV molecule which I showed you. And in this system, we have two molecules. One is the donor molecule system, and the other is the acceptor. So for this reason, we need to do a process which is called annealing. Annealing means the polymers need to reorganize themselves. And for this, we use just a hot plate, which has the temperatures of around 130 degrees. And I just removing the sellotape, because it will get melted on this temperature. And then I will just put the glass here on top of the heater. And we have to wait a couple of minutes. And what is happening in this time is that the donor molecules reorganize to each other, and the acceptor molecules reorganize, and they form so-called pathways for the charge carriers. So holes and electrons can better be transported to the electrodes. Yeah? So this is the reason why we need to come up with this heating process. Meanwhile, I would like to show you one thing. We can try to measure what is the solar activity of our OLED. Is our OLED also a good solar cell? So I just use here a multimeter, and I touch this multimeter to this OLED. And now let's see if we can get out a voltage. So yeah, you can see there's a very, very little voltage. I have a torch here. I try to. Oh, there's not much happening. Wait. Maybe the connection is not good. I will try the other one. Oh yeah, there was. I think there's some loose contacts here. There's happening at least a bit of things. Let's measure the current flow, and you will see there's no current flow. So this is actually something which I was expecting. So an OLED is not a good solar cell because it is trained to emit light and not to absorb it and to perform electrical energy. So remind these numbers. So we were almost around 0, because I would like to show you. I need my alligator clips. I will just take them, these ones. How it is when we use the solar cell. So I'm now taking the glass out of the hot plate. It's very hot still. And I'm preparing the electrode, the metal electrode. We have here, again, this mask. And this time, because I would like to have a bigger surface area to gain more electrical current, so I will just use one big spot instead of 3 small. So the good thing is I can reuse this material, the Galenstan. So now.
That is an insulin syringe, right?
Sorry?
The syringe is an insulin, standard insulin syringe, 40 unit insulin.
Yes, yeah. So as you can see, the spin coating process here was not very good. There are some lacking spots left here, but as long as the middle of the glass is covered, everything is fine. So I'm now putting it together. Still a little bit hot, so okay. And I'm clipping it together. So now you see this is our solar cell, and let's see if I can measure anything here. I think the contacts are very rusted. That's why it's not working so good. But let's see. Maybe this will work better. First, the voltage check. You can see the numbers, yeah. Okay, I think you could see that already without shining. I have an idea. I will use just some extra clips here. Then it should go better. Wait. Okay. Okay, now we have like 20 millivolts, and now I use the torch. Okay, I have connected as white wire. Thank you, thank you. 500. And also the current flow. Okay, the current flow is also there. You see, it's 600 microamps instead of 1 or 3. So this is a very potent solar cell. Unfortunately, sometimes I think the heating temperature was not quite enough because normally I should reach 2 milliamps. And if I have 2 milliamps, I would be able to run this fan, which is always more mazaya than just. But let's try anyway. Maybe it will work. And it's only the multimeter which was not working well. I will try it, but I don't think it will work. So 1 and 2. So let's see if we can run this fan. So, okay, let's see. Oh, it's running. Thank you so much. And it's always more fun if you do it yourself. So all these experiments actually are built to engage you. Active learning, we heard about that. So, yeah. Madaya, tick, tick. Huh? So I don't need the video. So I have I got 10 more minutes, hopefully. Yeah. So I would like to show you some more insights. So this part I will go through very quickly. We also do qualitative and quantitative research, of course. Yeah? We use research methods to, we follow the design-based research principle, and our outcome doing this research are reliable hands-on experiments, user-oriented teaching material, because I didn't had the time to tell you more about the teaching materials. Of course, we don't only want to do the experiments, we want to learn about the theory behind it. And we have a lot of teaching materials also generated and tested and evaluated. And at the end of the day, we came up with the instrumentation, because all these materials, these fancy materials, you cannot buy it outside. As a school, you are not able to buy it. So what we have done is we formed an experimental kit. Actually, I have one here, which contains everything you need to do these experiments in a classroom setting, not as a teacher demonstration setting, but as a classroom setting. And also, unfortunately, we cannot give it out for free. It's a transfer project of the University of Potsdam. But in Germany, for instance, we have the industry, which is sponsoring these kits to schools. We have cooperations in this. And also, Arnab, you have 10 of these kits. So if someone is enthusiastic in chemistry and physics or semiconductors, you can just ask Arnab to give you one of these boxes and to do these experiments with your students. So I would like to use the remaining time to, first of all, thank you. This was a picture back in 2017 when we did some teacher workshops also here in India and educated some teachers from different institutions. Also, we had a session here at the HBCSE. And we do all these kind of teacher trainings also in Germany, all over Germany, to disseminate these new findings. So I would like to introduce you two more topics. One is the hydrogen technologies. So when the Ukraine war started in Europe, then the problem was that Germany and the other countries realized we have to be independent from fossil energy sources. So hydrogen technology became a big thing in the last years. And we also thought about teaching hydrogen technologies in schools, and we found that there are a lot of systems to use, but nothing was very convincing and low cost. There were many systems which were very high cost, and so we came up with a very, very low cost, or I can say no cost, water splitting electrolyzer cell and a fuel cell. And I would like to introduce it very quickly to you. So the first thing is you normally use the Hofmann water splitting aperture in Germany to teach electrolyzers. So what we did is basically we replicated this in a very mini format, and we just used a tic-tac box. And we emptied the box, and we took some stainless steel nails and just melted in the bottom of the box. And so we got our electrodes, and we sealed it with some silicon, and we attached copper strips as contacts. And in this way, we have our low-cost mini electrolyzer cell, which is less than €1 when you buy the materials. If you just reuse the materials, it's no cost. And I would like to show this to you in an experiment. So this is also a live feed. I hope it's still working. Yeah, this is the electrolyzer cell. You can see here, I already poured some sodium hydroxide solution into it. Here we have the copper contacts, and I'm just attaching a 9-volt battery to get the system started. So and now you see the electrolysis is going on, and we thought about how to catch the gases and indicate that it's oxygen and hydrogen which is produced there. So we came up with the idea just to use these mini vials. Yeah, you can buy them also, or just I learned that here this homeopathic vials. Yeah, you can get here same size. So we just put it on the nails like here and there, and then you can see we are catching the gases. And after a while, you will see here. The double amount of hydrogen as oxygen has been captured. And this is very easy to do. Students engage them. They can do it themselves. And so I'm now using here a PowerPoint feature, which is new, which is Cameo. I can now use the live video feed and attach some more information, like we have here the positive pole and on the right side the negative pole. And we are using, it's in German, we are using a sodium hydroxide solution. So we go closer to the system. So here you can already see the 2-to-1 ratio here at the gas phase. What is happening on particle level here? And this is something which we also do. We engage teachers to do PowerPoint animations, because with PowerPoint you can easily do some nice animations which explain what is happening on the particle level. So on the positive pole, hydroxide ions are oxidated, giving 2 electrons each, so 4 electrons in total. And these electrons are given to the electrode. So oxidation is happening here, producing oxygen. The oxygen is released, and we have H+ ions, which are bound to the remaining hydroxide ions. So this is the process on the anode. And on the cathode side, this is the next animation. So this is a nice feature because you have still the live video feed going on, and you just show what is happening on the other side. So here we have 4 hydroxide ions being reduced and producing hydrogen gas or hydrogen molecules. and you get 2 hydrogen molecules instead of here was only 1 oxygen molecule, and the remaining hydroxide ions are just released into the solution. So now we can try to indicate the gases. So I will use here. Let me just return to the other view. Sorry, I haven't prepared this. Back, and this slide. Yeah, so we have a better view. So I have now here, okay, I will just hold it in the hand. So now I have here hydrogen gas. And the nice thing is, maybe someone can help me and just hold the candle. Okay, so I have now here hydrogen gas in this vial, and I need to remove the water film which is blocking here the gas. So I will just remove it, and then it will not be very loud. This is all because it is maximum filled with hydrogen. So this is lacking of oxygen. So what we now do is we just take this one, because this is filled with, we don't need this, sorry. Okay, thank you. So what I've done is I changed this one to this electrode. So now it was full with oxygen, and now I'm letting in some hydrogen. To be more accurate, it is better to start with a full bottle and to wait until you have only 1/3 of the water left, or electrolyte, and then change the electrode. Actually, I was talking too much, so I missed this moment. But let's try. Hope maybe it will also work like this. So now, maybe it's enough. Let's see. 3, 2, 1. No, it's not working. Okay, we can do it again. It's not a problem. Just. So I'm leaving some air. So you can also use air and just filling hydrogen into the bottle. And while this is filled, I'm just going to quickly show you the last thing I would like to talk about. We also developed a DIY fuel cell. We exchanged the 2 glasses by using stainless steel wool, and the stainless steel wool has a very big surface area. And in the surface area, the gases get absorbed, and in this way we can store the gases and have something like a fuel cell. We just need a separator so these don't get in touch and short circuit. I will also show this in a minute, because I think now you can maybe see here there's a little bit of water still left, so sodium hydroxide, and I can now try again. So this can be also an engaging task for the students, how to get a bigger boom. Yeah, so who gets the loudest explosion out of it? And then 3, 2, 1. Yeah, okay, thank you. So if you allow me, just the last thing I would like to show to you is, so I just talked about the fuel cell. And for the fuel cell, I just need this small piece of a sponge. It's just a small piece of a sponge. I insert it in between both electrodes. And now I'm going to increase the surface area of both electrodes by just using a stainless steel wool. You find these things in hardware stores or supermarket. It's just for scraping, yes, your dirty dishes and so. So okay, we just pour it on top of this. Put it on top of the electrodes. So and this way we increase the surface area. And now I just fill it back with the electrolyte, and I start the electrolysis. So this is the charging of the fuel cell, and maybe you can see that a lot of gas is going outside the system, but a lot of gas is also being absorbed at the high surface area of the electrodes. Yeah? And this absorption we can utilize, and I will now try, let's see if it will work, again to drive this small fan. So I'm just going a little bit outside this viewpoint. So, and now I'm connecting the propeller again. Let's see if this will work. Yeah, and you can see the fuel cell is working. So yeah, it's not a scam. So you see. So yeah, you can see Mazaya. Yeah, so all the time we try our best to develop these experiments as much as possible. The last thing I just quickly want to show you is another approach, which is automation. Automation is a big role in industry. In research labs, everything is automatic. Nothing is done by hand anymore. We can discuss if it's good or bad, but what we wanted to do is we wanted to bring this technique into classroom. And for this, we use a Lego system. And Lego has a very big advantage because in Europe, the students, they grew up with Lego. And here what you can see is a Lego titration robot. This is a burette containing HCl solution, and this is a beaker containing NaOH solution with the indicator bromothymol blue, which is blue when it's a basic solution and yellow when it's a acid solution. And the robot has two main features. It has a hand which can be used to turn on and off the. Sorry, my pointer is lacking. Hand to turn off and on the knob of the burette, and it has an eye color detector which can detect which color it's currently seen here. And the programming of this robot is also very easy because we have a block language. It's just a graphical programming language. And I would just like to show you a small video of the robot in action. You can see we turn the knob by 180 degrees, and in this way only one drop is released. And when the neutral point is reached, it is detected here by this eye.
Die Titration wurde erfolgreich beendet. Die Lösung ist jetzt neutral.
So in this way, playful, active learning, Mazaya, so all these things we look for, and I don't want to end without some acknowledgements. First, to my team back in Potsdam. Without them, I won't be able to do all this research. To my former alumni, cooperation partners, also the people giving us money. Here's the literature, and last but not the least, thank you for your attention.
Thank you, Amitabh. Thank you for a wonderful talk and the experiments. Now, questions, please. Yeah, please.
Thank you so much for this wonderful talk. So I have 2-3 questions. I'll get connect with you later then. But as of now, first is the P dot you all have synthesized in your lab, right?
The P dot PSS?
Yes.
No, we have a route we can synthesize ourselves, but actually for the suitcases we want a standard quality, so we buy it. Yeah.
Okay. So are there any regulations, and when you supply it to other schools, so all?
For the P dot PSS? No.
Yes. No. Okay.
No. There are
and
no
the
rules.
second about the semiconductor also, synthesized or commercial?
We have a route for synthesizing our own, but we buy it because we have special prices from for instance, when we buy it from Merck. But the semiconductors we are only selling as a solid component because we are not allowed to ship the solvents.
That's why I was asking.
Yeah.
Okay, I'll get connect with you later.
Yes.
Thank you so much. Yes.
Yeah, no problem.
Okay. Dr. Arun Kumara.
It's a very wonderful demonstration. Actually, I want to ask a question that what is because a molecule is said to be a semiconductor, I think it is the HOMO-LUMO gap.
Yes. Yeah.
So
I neglected that today in my talk.
Okay.
But normally we refer to the HOMO-LUMO gap,
Yeah.
and we have a special models which we introduce to the students how they can easily understand or more facilitatedly understand what is a HOMO and what is LUMO.
For photovoltaics, what is the optimum range of the HOMO-LUMO gap so that we can?
So we are always looking for narrow band gap, because if you wanted to use it outside via sunlight, then you go always, for instance, silicon has 1.1 electron volts, and this is something we are looking for. Yeah. So low band gap or infrared band gap semiconductors are the most efficient one if you are using sunlight.
Okay. Is there any quantitative study on that so that we can decide that this molecule can be used as a better for the photovoltaics or OLED? Because I'm working on this basically simulations.
Yeah.
So I can work with the molecules. So
I think this question you should address to physicists, for instance. I think, Arnab, you could also give work about semiconductors and their quantitative studies. But there is a lot of publications.
I'm just talking in context of the molecules. In context of solids, a lot of literature is there.
Okay.
Yeah. So for experimental point of view, I want to simply just for the sake of knowledge.
Yeah. So we didn't analyze the molecules, for instance, because this is not what we are looking for. Okay. We can afford to neglect things like band gap, to neglect things like lifetime, efficiency, because this is not what we are looking for. We are looking for what is reliable and can be done low cost, low risk, low time, and so on.
Yeah. That's great. Thank you.
No problem.
Yeah, Arpan.
I have a couple of small questions. So this organic semiconductor that you referred, is it biodegradable?
No. So this one is not biodegradable, but there are approaches to use semiconductors which are either synthesized using biomaterials, so natural products, for instance, or also some are biodegradable, but not the ones we use, because in this case we need reliable materials which show a very good performance in a very quick and dirty approach like we did. Yeah? That's why we are, until now, we are using these materials. But actually, I'm always looking for better or new materials because the research is still going on in this field. Yeah? For instance, a very new approach are perovskites, to use perovskites. We also have done some attempts to use perovskites in our system. The problem with perovskites is the most efficient ones are based on lead, and this is not possible to use it within a student experiment. We have used some lead-free perovskites, which is based on silver bismuth, silver and bismuth iodines, which showed a good performance, but it's very difficult to handle these materials. So we are still working on that to bring it from a prototype stadium to a very reliable experiment. So a Messiah experiment. We are still on the way.
The thing is that like all the materials that are needed to synthesize these organic semiconductors are they? I mean, there are other infinite resources in the sense like when you have metals or something that is finite resource on the earth. But like if like the materials that go into synthesis of this, are there like plenty in a sense?
Let's talk about this later. Maybe it's too much in the detail. Maybe this question, but we can talk about the synthesis. I have some slides, but I would like to show it later to you. Okay. Thank you.
Satish.
Hi, Amitabh.
Hi.
Nice talk.
Satish.
So, yeah, I was wondering if those instructional material that you showed, is it downloadable for free or is it just...
Yes, this is downloadable. I can give it to you, but is there some kind of a cloud or...
yeah, we can share it.
Yes, of course. Yeah.
Okay, great.
So the materials are all free, only the hardware you have to pay something.
If you can procure those things, we can do it by ourselves, right?
Yes, of course. Yeah.
So, and another question is, you tried these demonstrations only with school students, or like have you also tried with undergraduate students? I mean, at least
undergraduate
entering.
Yes, both. Yeah.
Okay.
So our main focus are school students, high school students, because all these topics are taught in Germany in schools.
Okay.
But we also have attempts in undergraduate projects with undergraduate students. Yeah.
Okay, great. So one more question, brief question.
Please.
So are there any plans of developing these kind of experiments for UG level, like if little more advanced maybe?
It depends on the topics. For instance, the hydrogen topic is something we can also easily do in the UG. For the organic semiconductors, it's very high standard. So also the techniques like spin coating or ductor blading, you can do it with special trained students in the UG. Okay. Yeah, but normally, the hydrogen kit, I think this is also something which you easily can use in an undergraduate.
Okay. Thank you.
There's a question. Yes, just wait for the mic, then everybody can hear it.
See, you have explained the philosophy of how you have developed or the principles. I would like to hear more about the instructional material, which you have developed and how you have gone about it. Mm-hmm. And if you have used it, what is the feedback? I mean, say how really went about the development of the material, because that is more to do with, lot to do with learning. So I'm a bit interested in knowing.
Yes. This will be another talk, actually. I would need another 45 minutes just to explain how we did our research about developing these teaching materials. So we have kind of a lot of teaching materials like animations, worksheets, lab manuals, and so on. And this was a PhD project. So my PhD student developed these materials, and in a design-based research cycle, we evaluated it along with students and also teachers. We got feedback from the teachers, and we got insight into student thinking. For instance, misconceptions. For one misconception is that the positive charges are related to protons. They always say protons are going from here to there and so on. And we first needed to understand that what is the learning difficulty, and then we had some approaches to come over with these difficulties. So to help them to understand what is a whole and what is the movement of a whole. Yeah? For instance.
Focused a lot on the misconception part of it, actually.
Not only the misconception, but this, misconception was one side product, let's say, which we could identify during our research about the teaching materials. Yeah.
Okay. Any more questions? Yeah. Yeah. Then Sonamni after that.
Chemistry involves a lot of chemicals which go into the nearby stream. We have that problem in the schools in Bhutan.
Yeah.
So how do you take care of the environmental aspect of, the disposal, and then which I might get some idea from you?
I can only answer in two ways. One is the general way, which is I talked about low scale. So, for instance, I could have also done this electrolysis experiment in a big demonstration, which has been done decades. Yeah, but I engage you to use these kind of things, which is if you want to show an experiment, for instance, which is just a mobile phone connected to the projector, and you can have a very small scale experiment using just 5 milliliters of sodium hydroxide. So in this way, you reduce waste, right? And also design your experiments, which you do with the students, as big as necessary and as small as possible. Yeah, so this is a format which we find out that students can handle this, and it only has a very limited amount of chemicals used. So also we have other projects which I didn't talk about today. One was treating wastewater with activated carbon, and this activated carbon we get from sugarcane waste. Yeah? It's a common thing which is done by industry, and we have developed an experiment how we transform the sugarcane waste to activated carbon and use this activated carbon to clean a dye solution, and then you will get just clean water. Yeah? So this is an explicit way to address environment-friendly activities. Yeah.
You'll have the final question from Sanamine. And
Yeah, actually, I have two queries. One is that about the danger of the fabrication of the hydrogen cell. If we, at say practical level, if we fabricate that and connect it in series and get more voltage, is there any danger if we use that, say putting that iron filing and all that?
Yeah.
Will it work, or that kind of cells are they exist in the market?
This technology which I presented is nothing we came up with. It's already established. There are a lot of hydrogen plants, at least in Germany. I think in India too, you have programs of building electrolyzers plants and hydrogen storage plants and so on. And to answer your question, of course, hydrogen is a highly flammable gas, so it has some potential of dangerous. But if you handle it with care and with profession, then it is a very safe energy source. Same thing with nuclear energy, for instance. It's a big thing in Europe going on. Turn off the power plants, and also, of course, there's always a danger attached to some things, but if you can control the danger and if you have security measurements, then you have a very reliable and a good energy source you could have. And this is where research has to be done to make, for instance, hydrogen a better, a more reliable and more safe energy source.
Okay, thank you. With that, we will end the session. Let's give a big round of applause.
Thank you so much.
Thank you, Amitabh.
We'll take a 10 minutes short break. I think you can remain here. Yeah, but let's do it.
I think we can continue.
Good.
I will just take this.
Take your time, don't worry. It's fine.
Thank you.
Sir.